Right now, like as you sit here listening to this deep dive, there are actually tiny atomic explosions happening inside your own body.
I mean, yeah, it sounds wild when you put it like that, but it's completely true.
Right. Trace amounts of potassium in your muscles are just spontaneously rearranging themselves. They're firing off these invisible bursts of energy right this second. And yet, you are perfectly fine.
More than fine. You're exactly as you should be.
Exactly. But if we mention the actual word for what's happening in radioactivity,
Mm-hmm.
it instantly makes most of us tense up. It immediately conjures up these intense images of, I don't know, glowing green hazard signs, invisible menace, and just catastrophic disaster.
Oh, totally. It's got the worst PR in science.
It really does. So today, we're going to completely reframe what is arguably the most terrifying word in the English language. We're stripping away the sci-fi monster dread to look at what radioactivity actually is.
Right, which is just a perfectly natural physical process, one that's older than the Earth itself, incredibly useful, and like you said, happening right inside you.
And if the word radioactivity brings back, traumatic memories of high school physics, or if you feel like you just don't have the science background for this, you can completely relax.
Yeah, you really don't need any prior science knowledge for this conversation.
Wow.
We are taking this nice and slow, breaking down the mechanics step by step.
Because our mission today is for you to walk away feeling empowered, well-informed, and maybe even a little bit in awe of how the universe balances itself out.
That's a great way to put it. Balance is really the key to all of this.
So to understand why we shouldn't blindly fear radioactivity, we actually have to zoom way, way in. We need to leave our human-sized world behind and look at what is happening on a microscopic level. It all starts at the very center of an atom, right in the nucleus.
Yeah. So picture that nucleus. It is incredibly tiny, incredibly dense, and made up of two types of particles packed really tightly together. You've got protons, which have a positive electrical charge, and neutrons, which basically have no charge at all.
Okay, so protons and neutrons.
Right. Now think about magnets. If you try to push the positive ends of two magnets together, they repel each other.
Yeah, they slide away from each other.
Exactly. Protons do the exact same thing. Because they are all positively charged, they actually want to violently fly apart from one another.
But if they all want to fly apart, there has to be something holding them together.
Hmm.
Otherwise, every atom in the universe would just instantly explode.
Right. And that is where the neutrons come in. They act as a sort of glue. There is this phenomenon called the strong nuclear force.
The strong nuclear force. Got it.
Yeah, and it operates like a microscopic, just incredibly powerful bungee cord tying all those protons and neutrons together. It completely overpowers the proton's desire to push apart.
Oh, wow.
And
Wow.
in most atoms, this balance is just perfect. The bungee cord holds everything in a nice, stable, comfortable state, essentially forever.
But in some atoms, that balance gets out of whack, doesn't it?
It does,
Yeah.
yeah. The combination of protons and neutrons becomes a bit lopsided. Maybe there are too many neutrons or maybe too many protons.
And because of that lopsidedness, that bungee cord is stretched to its absolute limit.
Precisely. The nucleus is holding on to just a little too much tension and energy. It isn't settled.
And nature, as a general rule, dictates that everything must eventually find balance, right?
Oh, absolutely. A lopsided nucleus holding all that tension, it isn't going to stay that way indefinitely. Sooner or later, that bungee cord is going to snap, or at least, aggressively shift.
So the atom forcefully rearranges itself to reach a more stable, comfortable state.
Yes, exactly.
So is it kind of like an overpacked suitcase? Like you've stuffed way too many clothes into it and you're sitting on it to force the zipper shut?
Oh, I love that analogy.
Yeah. And the whole thing is bulging and unstable. Eventually, the pressure is just too much. The zipper bursts open like a pair of socks shoots across the room. And finally, the suitcase can relax into its normal shape.
That is exactly the mechanism. The bulging suitcase is the unstable atom. The bursting open is the event itself. And that sock shooting across the room, that's the excess energy or particles being thrown away.
Okay, so let's define our terms here, because I feel like people use these words interchangeably all the time, which causes so much unnecessary confusion.
Yeah, it really does.
So the overall process of the atom transforming from lopsided to stable, the whole suitcase ordeal, is called radioactive decay.
Right.
The actual event, the spontaneous bursting of the atom, is radioactivity. And the sock, the physical particle or the burst of energy that actually gets flung out and travels through the air, that is radiation.
Separating those concepts really makes everything else click into place. Radioactivity is the action, radiation is the stuff emitted, and radioactive decay is the overall transformation.
It takes the malice out of it, I think. It's not some monster trying to get you. It is literally just physics trying to relax.
Trying to get comfortable.
Exactly. But since we know the atom is throwing off this energy just to get comfortable, we really need to look at what exactly it's throwing out, because understanding the different types of socks shooting out of that suitcase is the absolute key to understanding safety.
For sure. Because a decaying nucleus doesn't just throw out one type of thing. There are three main kinds of radiation that can be emitted. And they differ wildly in how heavy they are, how fast they move, and crucially, what it takes to stop them.
Okay, let's walk through those three flavors. The first type is what physicists call alpha radiation, right?
Right, alpha. And from a microscopic perspective, an alpha particle is massive. It's really heavy, and it moves relatively slowly.
Because it's big and slow, I'm guessing it bumps into everything in its path.
It does. It loses all its energy very quickly, just trying to push its way through the air. Therefore, it can be stopped by something incredibly flimsy, like a single sheet of paper will stop an alpha particle.
Wait, really? A sheet of paper?
Yeah. In fact, just the dead outer layer of your own skin is entirely enough to block it completely.
Okay, wait, let me push back on that for a second. If alpha radiation is so weak that my skin just bounces it off, why do we even care about it? How could that ever be a hazard?
Ah, that is the crucial distinction. Because it can't penetrate your skin, alpha is only a hazard if you breathe it in or swallow it, or if it somehow gets into an open wound.
Oh, I see.
Yeah, once it is inside you, past that protective barrier, it is right up against your soft, living tissue.
It would be like letting a bowling ball loose inside a china shop. Outside the building, the bowling ball just hits the brick wall and stops. But if you put the bowling ball inside the store, right next to the delicate glassware, and let it roll, it's going to smash everything it touches.
Exactly. Inside your body, that heavy alpha particle dumps all of its energy directly into your delicate cellular machinery and your DNA, which causes severe localized damage. Context is everything here. Outside the body, completely harmless. Inside the body, highly destructive.
Okay, that makes total sense. So if alpha is stocked by skin, what about the second type? This one is called beta radiation, right?
Yes, beta. Now, beta particles are much lighter and they move a lot faster than alpha particles. Going back to your analogy, if alpha is a slow-moving bowling ball, beta is more like a golf ball moving at high speed.
So a sheet of paper isn't going to do the trick here.
Nope. The beta particle will sail right through paper, and it will easily pass through the outer layers of your skin into your tissue. But it can still be blocked. You just need a thin sheet of metal, something like aluminum or a specialized plastic, to stop it in its tracks.
Which brings us to the third type, gamma radiation. If alpha is stopped by skin and beta gets stopped by thin metal, gamma is the one that just blasts right through almost everything.
Yeah, gamma is intense. And the crazy thing is, gamma isn't made of physical particles at all.
Wait, it's not a particle?
No, it is a very, very high energy form of light. It's similar to X-rays, but with even more energy. And because it is pure energy with no mass, it is extremely penetrating.
Wow.
It's like a blinding flash of light that can pass right through walls. Paper does absolutely nothing. Thin metal does nothing. To stop gamma radiation, you need thick, highly dense materials to absorb all that energy. We're talking thick slabs of solid lead or several feet of dense concrete.
Which completely explains why safety gear in the medical field or like the nuclear industry varies so much. Radiation isn't just one single thing. It's a whole family of behaviors.
Exactly. You have to match the shield to the specific hazard. If you are a dentist taking a high-energy X-ray, which acts very similar to gamma, you put a heavy lead apron over the patient to absorb those penetrating rays.
Right, the lead apron.
But if a lab tech is handling an alpha-emitting substance, they don't need a giant lead wall. They just need basic gloves to keep it off their skin and a mask to make sure they don't inhale it.
Understanding that difference is really what separates this irrational blanket fear of all radiation from practical everyday safety.
Oh, 100%.
So this understanding of how atoms decay, these lopsided atoms seeking comfort by throwing off alpha, beta, or gamma radiation, it leads us to an incredible concept.
Yeah.
It is the story of how a completely random, chaotic event transforms into a perfectly reliable clock.
This is honestly my favorite part. It deals with the transition from total unpredictability to absolute certainty.
Okay, lay it on me.
Let's think about one single unstable atom. As we established, it is lopsided and wants to decay to reach stability. But you cannot predict when that specific atom's bungee cord will snap. It is pure, total chance.
Really, there's no way to know.
None. That single atom might decay in the next literal second,
Yeah.
or it might sit there wobbling for 1,000,000 years before it finally bursts open. It is utterly unknowable.
But in reality, we are never dealing with just one atom, are we?
Right. In any real-world lump of material, a grain of sand, a piece of bone, a drop of water, you are dealing with billions upon billions of atoms.
And when you have a massive group of atoms, their collective behavior suddenly becomes astonishingly irregular. It's kind of like flipping a coin, right?
Yes, exactly like that.
If I take a quarter and flip it one time, I have absolutely no idea if it's going to land on heads or tails. I could guess, but I don't know. But if I gather up 1 billion coins and I dump them all on the floor at the exact same time, I know with absolute mathematical certainty that almost exactly 50% of them will be heads and 50% will be tails.
Exactly. The randomness of the individual creates a perfectly predictable group, and in radioactivity, we call this predictability the half-life.
The half-life. Okay, let's define that.
The half-life is the exact amount of time it takes for exactly half of the unstable atoms in a sample to decay and settle down.
So let's walk through that rhythm. Say you have a lump of radioactive material. After one half-life passes, exactly half of those unstable atoms will have decayed into a stable form. The other half remain unstable.
Right.
Then you wait for one more half-life to pass. Now half of that remaining half decays. So you're left with a quarter of your original unstable atoms.
Another half-life goes by and you're down to an eighth, then a 16th. It just keeps halving right down the line. And this rhythm, this halving process, is rock steady. It is unique to each specific radioactive substance.
Meaning different substances have different timers?
Exactly. Some substances have a half-life of a fraction of a second. Half of it is gone almost instantly. Other substances have half-lives that take thousands of years or even billions of years. But whatever the substance is, its specific half-life never changes.
You literally can't mess with it.
Yeah.
You can't speed it up or slow it down.
Yeah.
Like you can heat the material in a furnace, you can crush it under immense physical pressure, you can dissolve it in harsh chemicals. The atom simply does not care.
It really doesn't. The nucleus is buried so deep inside that external forces just don't affect it. It just keeps ticking at its own unchangeable rate.
Which means every single piece of radioactive substance in the universe is essentially a tiny, perfectly reliable stopwatch that started ticking the moment it was formed.
Yes, and because we figured out how to read these atomic clocks, it has completely revolutionized how we understand our own history. This is how radiometric dating works.
Oh, like carbon dating.
Exactly. If you know the half-life of a substance, you can measure how much of the radioactive material is left compared to what it started with and calculate exactly how long that decay has been running. You can tell exactly how old an object is.
Let's talk about carbon dating, because archaeologists use that all the time.
They do. So high up in the atmosphere, cosmic rays create a slightly radioactive version of carbon called carbon-14. It has a half-life of about 5,700 years.
Okay, 5,700 years.
Right. Plants breathe this carbon in, animals eat the plants, and humans eat the plants and the animals. So while you are alive, you are constantly taking in a tiny, totally harmless amount of carbon-14. Your ratio of normal carbon to radioactive carbon basically matches the environment.
But the moment you die, you stop eating. You stop taking in new carbon-14, so the clock starts.
Exactly. The carbon-14 that was already inside your bones slowly starts decaying, turning into nitrogen, having every 5,700 years.
So thousands of years later, an archaeologist digs up a bone or maybe a piece of wood or ancient cloth. They measure the ratio of carbon-14 left in the sample.
Right. And because they know exactly how fast that clock ticks, they can calculate exactly when that plant or animal lived and died. It allows us to date human history back tens of thousands of years with incredible precision.
But the time scale goes way, way further than ancient human history, doesn't it? Geologists look at entirely different radioactive substances locked inside rocks to date the Earth itself.
They do. Take uranium, for example. It decays into lead over a half-life of about 4.5 billion years.
Wow, 4.5 billion.
Yeah. And geologists can find these microscopic, incredibly durable crystals called zircons in ancient rocks. When a zircon crystal forms in cooling magma, its chemical structure is really happy to trap uranium inside it, but it completely rejects lead.
So it acts as a perfect sealed time capsule.
Exactly. So when a zircon crystal first hardens, it has uranium but absolutely zero lead. If a geologist grinds up that rock billions of years later and finds lead trapped inside that crystal, they know without a shadow of a doubt that the lead wasn't there at the beginning.
It had to come from the radioactive decay of the uranium.
Yes. And by measuring the ratio of uranium to lead, they've been able to measure the age of the Earth at 4.5 billion years old. Without these atomic clocks ticking away inside the rocks, deep time would just be total guesswork.
We are literally reading the diary of the planet written in the language of atoms.
I love that. Yes, exactly.
But this brings up a really practical question. If radioactive decay is constantly happening in the rocks around us, if it's been happening for 4.5 billion years to cut these clocks,
Yeah.
what does that actually mean for us living our everyday lives on this planet?
That's the big question.
Because we hear the word radiation and we just assume it's an artificial poison created in a lab. How worried should we actually be about radiation in our daily lives?
Well, the honest answer is far, far less than its reputation suggests. I mean, it absolutely deserves our respect, especially in concentrated forms, but we do not need to walk around in fear. The key fact that completely changes the perspective is that radiation is entirely natural and it is everywhere, all the time.
We are practically swimming in it, aren't we? We are constantly exposed to what's called background radiation.
Yeah, background radiation.
It is coming from the rocks and the soil under our feet. It is coming from cosmic rays, raining down on us from outer space and interacting with our atmosphere. It's in the air we breathe. It's in the food we eat.
Bananas are the famous example here. They contain potassium, and a tiny fraction of all potassium in the universe is a naturally radioactive isotope. When you eat a banana, you are taking in a minuscule amount of radiation. Because of the food you eat and the air you breathe, there are naturally radioactive atoms decaying inside your own body right now.
It's honestly, it's jarring to hear that. Hearing there is radiation in our food and inside our bodies triggers that old fear reflex.
Of course it does.
But we have to apply the concept of proportion. Treating radiation with proportion makes so much sense. It is the exact same way we treat water or sunlight.
Oh, that's a great comparison.
Like, water is essential to life, and a glass of it is perfectly safe. But if you are submerged in a flooded river, it is highly hazardous. Sunlight warms the earth and helps our bodies synthesize vitamin D, but if you bake in it for 10 hours in the desert without protection, it will severely damage your skin.
Right.
Radiation works by the exact same logic. It's naturally present in normal amounts, but hazardous in extremes.
And that is the mindset that replaces fear with appreciation. Biology on Earth evolved amid this background radiation for billions of years. Life has always existed in this environment. At these ordinary, everyday levels, it is simply part of the natural world.
And our bodies adapt to it.
Completely. Your body has incredible cellular repair mechanisms that know exactly how to handle and repair the tiny, occasional bits of damage caused by natural background radiation.
So the danger purely comes down to dose. How much radiation are you getting? How intense is the source? And for how long are you exposed?
Exactly. Very high doses, the kind you would see in a serious nuclear accident, or if someone was carelessly handling incredibly strong, concentrated radioactive sources without the proper lead or concrete shielding. Those are genuinely dangerous. They will overwhelm the body's repair mechanisms and damage living tissue.
But the trace levels we meet day to day are negligible. Even a carefully controlled dose from something like a medical X-ray or a CT scan carries a very, very small risk.
Right. And in medicine, that tiny risk is almost always far outweighed by the massive benefit of finding out exactly what is wrong with you so it can be treated.
And it's worth highlighting how much actual good this phenomenon does for humanity. We aren't just surviving it, we are using it to thrive.
Oh, absolutely.
In medicine, we harness gamma rays to sterilize life-saving surgical equipment, ensuring there is absolutely no bacteria left on a scalpel. We use targeted bursts of radiation to destroy tumor cells in cancer patients.
And over in the industrial world, they use penetrating radiation to inspect the internal integrity of thick metal welds on bridges, airplanes, pipelines, seeing deep inside solid steel to make sure it won't collapse. We have harnessed the ticking of the atom to build the modern world. It really is a foundational tool of modern civilization. Though I do want to add a brief note here.
Sure, go ahead.
We are discussing the broad physical concepts today. If you, listening to this, have a specific personal health situation, maybe you have an upcoming scan, a specialized medical treatment, or you have a concern about a specific exposure in your workplace, the best thing you can do is talk to your doctor or a qualified medical physicist.
Yes, that is incredibly important.
They can look at your specific dose and situation and give you the exact context you need. General knowledge is wonderful, but always rely on medical professionals for your personal health.
Absolutely. So let's look at the journey we've been on today. We started with a word that usually makes people want to run in the opposite direction. But when we broke it down, we saw that at the very heart of the matter, Radioactivity is just lopsided atoms.
Suitcases stuffed with too much energy.
Right, just trying to drop some of that tension so they can finally get comfortable.
Yeah.
We learned that the socks they throw out come in different flavors. Heavy alpha particles, fast beta particles, and pure energy gamma rays. And that shielding against them is a very practical, logical science.
It's all about context.
And we saw how the random chance of a single atom snapping transforms into the brilliant rock-steady rhythm of a half-life. That rhythm creates the atomic clocks that let us date ancient human history and read the 4.5 billion-year age of the Earth itself.
It's just amazing.
It really is. And finally, we looked at the reality of background radiation, realizing that we evolved in a naturally radioactive world and that dose and proportion are everything.
The transition from fear to understanding really is empowering. And I want to leave you with one final thought to ponder as you go about the rest of your day.
Let's hear it.
We talked about how there are naturally radioactive atoms, like trace amounts of carbon and potassium decaying inside your body right this very second. Because of those atoms, because of those tiny lopsided nuclei seeking comfort inside you, you are technically a walking, ticking atomic clock.
Oh, wow.
Every single time an atom inside you settles down and releases a tiny, harmless burst of energy, it is participating in a natural, ancient process. It is the exact same mechanism following the exact same laws of physics that allows geologists to measure the history of our solar system. Your physical body is intimately, fundamentally connected to the vastness of deep time.
That is incredible. The next time you hear the word radioactive, don't picture the glowing green goo or the hazard signs. Picture the ancient, quiet ticking of the universe, constantly working to find its balance. Thank you for joining us on this deep dive. Keep questioning the things that scare you, look for the quiet truths hidden underneath, and as always, stay curious.